Dear students, today we will discuss Taylor's series expansion. Taylor's series expansion for complex functions. We already are familiar with Taylor's series expansion of real functions, and here we extend that to complex functions. We shall need certain things that I would like to review a little bit. Perhaps the most important thing that we will need both for Taylor's series expansion and the Lorentz series expansion that is coming after this. In both of them, we shall need the a little knowledge, a little bit of geometric this series geometric series that you are already familiar with, you might be familiar with, but maybe you might have forgotten that. So here is a quick review of that. Suppose you have a series like this: 1 plus x square plus x cube plus x4 plus dash dash up to infinity. So this is a series for the obvious reasons. Okay, now this series has terms, okay, and this series, if we divide, say, this second term by first term, we will get a ratio that is equal to x. If we divide x square by x, we will get the ratio equal to x, and so on. So it is a constant ratio, and that common ratio is x. Okay. Now, without going into that, I will restrict myself to only as much as I need. So, suppose I want n terms of this series. Say I don't take all the infinite terms that I cannot take at all. Even if I spend my whole life on that, I won't be able to take infinite terms. Let me take n terms of this series. Say 1 plus x square plus x cube plus dash 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 xn. So xn. My question is, what will be the sum of this series? Let that be Sn. I denote that by Sn, sum of n terms. Now suppose I multiply Sn by x Sn. What will happen to this? This will become, when you multiply this by x, this will become x, this becomes x square, this becomes x cube, plus dash 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 dash, and here there will be a term that becomes xn, and then this last term when multiplied by x will become xn plus 1. This xn will be due to some term here, xn minus 1, and when that xn minus 1 is multiplied by x, it becomes xn. So now if I subtract this from the first, minus 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 minus, subtracting them, I get Sn minus xSn is equal to, this cancels with this cancels with this cancels with this, and so on. This cancels with this. You are left with x. We are left with 1 plus 1 minus x raised to n plus 1. Therefore, if I take Sn common, I get Sn 1 minus x is equal to 1 minus x raised to n plus 1. Therefore, Sn is equal to 1 minus x raised to n plus 1 divided by 1 minus x. Good. So, sum of first n terms of this series, this infinite series, is 1 minus x raised to n plus 1 divided by 1 minus x. Now, proceeding ahead, I will write it here. Sn is equal to, it was Sn is equal to 1 minus x raised to n plus 1, 1 minus x raised to n plus 1 divided by x raised to n, x raised to n, x 1 minus x, 1 minus x. Okay, now one term, this x raised to n plus 1. Suppose I take this separately, x raised to n plus 1. I have this x raised to n plus 1. Okay. If this x is less than 1, or greater than -1. This means if this x is confined to this, suppose x is confined to 1 and but not excluding the endpoints +1 and -1. That means if the value of x is restricted to this domain without excluding -1 and +1, the same thing can be written as x belongs to open interval -1 +1. When we write something like this, it means that neither this point nor this point is included. Rest of all the points are included. Now, if x has this value, then only the series that I showed you, this series 1 plus x square plus x cube plus infinite series, this will converge. If x does not belong to this interval, if it is -1 +1 or greater than +1 greater than -1, it will not converge. This series is very interesting. Had we been talking about convergence, we would discuss it in detail. It actually, this series is used to explain all the four types of these what we can call them convergence or series behavior of series, as number of terms in the series tends to infinity. We can explain with the help of this, we can explain convergence that I'm explaining right now. We can explain divergence. We can explain this oscillation, and oscillation of two types: finite oscillation, infinite oscillation. Most of the time, the students of physics and engineering, most of them are unfamiliar with real analysis, and either they are unfamiliar with because of the same is not included in their syllabus, or due to some other reason. Anyhow, but real analysis is the heart of mathematics, and most of the mathematics that we study, it is basically, it stands on the that on a layer, a sub layer, that is in VLSI technology we call it substratum. It's the substratum of all mathematics is real analysis in general, real analysis in particular, because once you understand real analysis, then it is quite easy to extend the same to complex analysis and so on. But real analysis is very, very important. However, I will assume that most of the students who watch this video, they are not familiar with real analysis, so I will avoid this real analysis. And in avoiding this real analysis, I will not at all compromise with the quality of this video, not at all, because I have to see, I have to use certain ideas from these real analysis, but I will not. My approach will be that I won't be going after theorems and proving them. My approach will be to appeal to your this common sense to understand that this really should happen. So let's go back, and without going wasting time, let's turn back to our focus. Let us shift our focus back to this. This is an infinite series, and if you have an infinite series, it means that it has infinite terms. And how wonderful it is when someone tells you that this infinite series, sum of this infinite series is, say, 10, for example, 10, or sum of this infinite series is 10 lakhs, 1 million, say 1 million. Sum of this infinite series is 1 million, for example, a finite thing. Now, infinite things added together, our mind says, our common sense says that they should total to up to infinity, that the sum of this infinite series should be infinity. But not always. Not always. It depends upon what you are actually summing up. If this x, as I told you, if the value of this x is such that its modulus is 1, that means its size is just 1. Minus, for example, -1, sorry, not 1, I'm sorry, less than 1. That means the x is confined to this interval. But what is there in this interval? All those fractions that you are familiar with, like say 1 by 2. 1 by 2 will be somewhere here. So suppose x lies between these two limits, then these two ends. Then say what this series will become: 1 plus, this is my example from this interval, 1 by 1 plus 2 plus 1 by 2 squared plus 1 by 2 cube plus 1 by 2 raised to 4 plus you can imagine yourself the increase with increasing power. Let us see what will happen. If we just consider these few terms, they will convey us the idea that I want to convey to you, that is 1 plus 1 by 2, that is 0.5, but 1 by 2 square, that is 1 by 4, that is 0.25, plus 1 by 8, it needs to be calculated anyhow, 1 by 8 plus 1 by 16. What do you observe? We observe that each new term is lesser than the previous term. That means that this is possible only because x is the x is with some number in from this interval. Suppose x had been somewhere from this, for example, it had been say here, from here say 2, it had been 2, the terms would increase. It would be 1 plus 2 plus 2 square, that is 4, plus 2 cube, that is 8, plus 2, that means it goes on increasing. Like that meiosis, when one cell divides, it gives rise to two cells, 2 give rise to 4, it is mitosis, sorry, 4 gives this, then 4 gives rise to 8, and so on. Now this series, if we include infinite terms, anyone among you and will come up with answer that the sum will be infinite, because it is complete. It is only increasing. It is increasing and increasing. It will never converge to any finite number. But what about this? Yeah, there is a chance that it will this decrease. It will go on. Sorry, there is a chance. No, it is actually decreasing. Each new term is that half of the, no, not half. Each new term is, yes, this is half of this, and this is, yes, this 1 by 8. This was 1 by 4, the 1 by 8, that is half of the 1 by 16, and so on. Yes, exactly. But important thing is that the size of each new term is decreasing. You can yourself think that when I reach, suppose 1, 2, 3, 4, 5, suppose when I include 100th term, you can yourself imagine what will be its size. Its size will be quite small, and addition of that 100th term will hardly change the sum that we have got up to 99 terms. Then the addition of 100th term will hardly change that sum. It is as if someone is pouring a glass of water into an ocean. The level of the ocean will hardly change. Now you can yourself imagine, if now we let n tend to infinity. Now suppose I will not talk about 100th term. Suppose I talk about 10 millionth term, 1 trillionth term, and then I'm sorry, I don't actually know what I have to say, how to count beyond that. Let us stop here. You can yourself imagine that when n tends to infinity, the size of the term tends to 0, and as the size of the term tends to 0, this means that we can, after some number of terms, we can discard all the rest and be content that we have got the sum of infinite terms. That which called such a series, as such a series is called a convergent series. On the other hand, this series is called a divergent series. That is what I wanted to say. So when does this series, this 1 plus x square plus x cube, when this converges? So we remember that whenever this x is, its size is less than 1, whenever it is less than 1, it will converge. Now, otherwise it will diverge or oscillate. We need not bother about it. At least we know it will converge only when this is there. And that is my point. That is what I am going to use. And where I will use that, just see. Suppose, first of all, let me use it here. Let n tend to infinity in this sum, n tend to infinity. If n tends to infinity, as I told you, this term will tend to 0. This term, this x n plus 1, because when n goes to infinity, the term there will have hardly any value, almost zero value. it will be 0, so I can drop it that at that time, and I will write sum of infinite terms of a geometrical progression is equal to 1 by 1 minus x, provided, for example, provided that x is, you must remember this, provide x is less than 1, mod x is less than 1. Now, so my dear, uh, we have now, let us go back to this, let's move forward now. We have one more thing to remember, that is, remember that is, see, power series. What is this power series? Power series. A function can be represented as a power series about some point. When we talk about power series, we say about some point. Power series about a point. Without this phrase, power series, if I just say power series, it is an incomplete thing. Just when we talk about electric field, that's an incomplete thing. But when we attach to it electric field at a point, that completes it. Now, similar here, power series at a point. At a point, we will see what it means. At a point, say A, point A. Now, suppose you have a function, complex function fz. Now, you can under certain conditions, of course, you can express it as a power series, as a polynomial. What is power series? Power series is basically a polynomial like expression of this form. Say you have, suppose fz is equal to co, a constant, plus c1 z, c1 z1, z minus a, z minus a, because you are expanding about a. Expanding about a means in powers of z minus a. Expanding about b will mean in powers of z minus b. Expanding about 3, for example, will mean expanding in powers of z minus 3. Expanding in about 0 will mean simply a powers of z. No minus or plus. So you are here expanding it in terms of c1 z minus a, then c2 z minus a whole square plus that dot dot. Now, with these things now, we can write the same in a concise way, as we can write it as summation n is equal to 0 to infinity. We have then cn z minus a raised to n. You can check it. If you have n equal to 0, n equal to 0 means c0. This 0 will mean 1. So the first term will be c0. Second term will be c1. Now n equal to 1. N equal to 1. Z minus a raised to 1. That is this. N equal to 2. C2. Z minus a raised to 2, and so on. This infinite series. Now, this infinite series, we have now one interesting thing, that every such series, we call it power series. Now, because of this power, these powers, power series, it is a polynomial expression of the function. Now, whether a function can be expanded in the power in this way or not, that depends upon, in complex analysis, that depends upon whether this function is analytical or not. An analytical function always has a power series, this expression. This, in fact, analyticity and power series expansion, they are, in complex analysis, they are same. Analyticity is equal to, we can say, analyticity is a guarantee that the function can be expressed as power series expansion, PSE, power series expansion, analyticity. Okay, now, whenever a function is expressed as a power series, we are going to prove this. Whenever a function is expressed as a power series, two things are important. That is, one, about power series always means about some point. About some point means you are expanding it in terms of that z minus that point. This is called center of expansion. It is called center of expansion. But A power series expansion of an analytical function is not necessarily valid at every point, about every point, or in every region or complex plane. No, it depends upon one thing. If a function is convergent, it does not mean necessarily that it will be convergent everywhere. Functions are limited by their range of convergence, their radius of convergence. Suppose, for example, suppose we have this complex plane, Okay, then I have a function like this: f z is equal to 1 by z plus 1, z minus 1, z minus 1. Immediately, when you look at this complex function, you find that it is singular at z is equal to 1. This is the only singularity that it has. Rest, it has no problem. For example, if you put it here, z is equal to 0 here. If it is valid here because it is 1 by 0 minus 1, that is minus 1. Okay, it's a finite number, minus 1. So z equal to 0 is not a problem here. Z is equal to 0.1, no problem. 0.1 minus 1, no problem. Then 0.2, no problem. Similarly, 10 minus 1, 9, 1 million minus 1, okay, no problem. But exactly at z equal to 1, it blows up. Now suppose this is 0, okay, and this is say z equal to 1 here. Z equal to 1, mod z rather, mod z equal to 1, okay. If it is here z equal to 1, mod z equal to 1, this means that this point is the singularity of our function. This point, at this point, it is not analytic. And if we take a circle of radius, this radius 1, of this radius, if we take a circle like this, then we say that this circle is the disk of convergence of this disk of convergence. Disk of convergence is that part of complex plane where a function is convergent. Where it is, sorry, where of course, yes, it is convergent, or if it is analytic. Disk of convergence means that area, that circular area in a complex plane where a function is this where it is analytical, and exactly at the boundary of the disk it is not analytic. At the boundary of the disk it is not. So this is called, this distance is called radius of convergence. So radius of convergence of this is equal to 1. This radius of convergence is equal to 1. Radius of convergence, we can think like this: radius of convergence of a function, radius of convergence of a function is the distance from the it is center of expansion. Suppose you are expanding it about 0, center of its expansion, up to the first singularity that you find. Suppose this is the center of expansion, and here is the singularity that you find. This distance between the two is called radius of convergence. Now we have, similarly, suppose I take some other example. Say I have 1 by fz is equal to 1 by 1 z square plus 1, z square plus 1. And there is, say, if you put it 0, no problem. However, z square is equal to minus 1 will make it 0. Z square is equal to minus 1. You can see it. Z square plus 1 equal to 0. That means z square is equal to minus 1. Z will be equal to root minus 1, that is plus minus I. So again, radius of convergence will be 1, because radius of convergence 1, because simple is that mod z will be 1, mod minus z will be 1, So again, and so every function has some radius of convergence. It is not that a function will be convergent throughout the universe. No, it will be convergent within some domain. There are, of course, examples of functions which have a radius of convergence equal to infinity. We will see. We will, of course, discuss those as well in problems. Now, with this thing that a function, a complex function in general, a complex function has a radius of convergence, and we have also given you the idea of what radius of convergence means. I will repeat once more that radius of convergence for a function is the this distance from the center of expansion of the function to the center of expansion of the function to the first singularity of the function, first singularity. So suppose we can now understand this. We are now ready to go for this Taylor series. Talking about Taylor series, we have, suppose as usual, we have say just a minute. Talking about Taylor series, so first of all, it all refers to a complex plane. We have a complex plane, and suppose this is our point of expansion, not necessarily origin. It is not necessarily origin. Okay, let me take it here. Suppose it is this our point of expansion, A. Because this would, if I had used this point, this would simply you would develop a concept that perhaps this a point of expansion is always zero origin. No, it is not must. You have a point of expansion here, and then suppose here is the this first singularity. We have this our this disk of convergence, and then this our radius of convergence. Or okay, let me take now 2 points, and I will this is A is center of expansion, about which we are going to expand the function. Center of expansion. That means, what does that mean? Let me remind you once more. Suppose the function is fz. I want to expand it in a series expansion where the terms will have different terms will have z minus a powers of z minus a. Second term will have z minus a raised to 1/3, z minus a raised to 2, and so on. That means expanding about a. Now one more, that is one thing, and one more thing now. There is one more meaning of this, but I will not touch that right now. One more thing, that is, I will use 2 points. One point within the disk, say, suppose here is a point, the point is z. Another point I will choose exactly on this what I call this boundary, exactly at the boundary. Here, this point that I am going to use on the boundary, that will be denoted by gamma. This is what we call this our this variable of integration. I am going to use Cauchy's integral forms in two forms. One will be the Cauchy's integral form, that normal form. Another will be the generalized Cauchy's integral forms. Say, for example, first of all, normal form CIF. CIF is, we must remember, we have to keep them written in front of us, because we will need them. Cauchy's integral formula is simply you have fz divided by z minus a, where a is point of singularity, is equal to that is equal to 2 pi i f a. This is one. Another is this that is generalized Cauchy's integral form. That is, I should say fz divided by z minus a. You have here higher order, but z minus a, we will write it equal to n plus 1. It is n plus 1, and then we have on this, there's dz. I'm sorry for this. It's dz, and then on this side I have something that I won't be able to write here right now. I will go a little bit this way, and then I will write it like this. I have fz divided by z minus a dz z minus a whole raised to n plus 1, n plus 1. This generalized Cauchy's integral formula that we have derived, it is equal to this value of this is equal to 1 by 2 pi. No, it is perhaps it is yes 2 pi I divided by n factorial fn a, yeah, n factorial, sorry, n factorial fn, that means nth derivative of this function fz evaluated at a. We will be using these two. So we start from this. Suppose I will need one more thing, something more here. But before using that thing, let me show you what I am going to do. I am I'm going to expand this function about fz function about a. And for that matter, I will be using Cauchy's integral formula here. First, I will start with Cauchy's integral formula. I will write fz is equal to fz, that means function within this disk at any point, is equal to 1 by, you have here fz dz is equal to sorry, this is 1 by, here this is 1 by 2 pi I, yes, 1 by 2 pi fi, 1 by 2 pi I fa that is yes, fa, or we can say it is, sorry, I will rewrite it this way, since I have chosen this variable here, variable of integration. This gamma is variable of integration. So that is not variable of integration. We're integrating along this, and integrating along this, basically this this integral. Say, let me first write Cauchy's integral formula. That is basically it is a line integral 1 by 2 pi I in line integral around this, say c, let this be the c, and then f and a, it is it is equal to fz f gamma. Gamma is the variable of integration, gamma divided by then we have gamma minus z d gamma. You must not confuse two things. One, that is variable of integration. Gamma is the variable of integration. This, it is variable of integration. Variable of integration means it is the variable that is defined for this boundary. You are taking this line integral along the boundary, and the variable that you are using is gamma, not z. Z is a point inside this disk, anywhere inside this disk, but between this boundary and A. Naturally, you can understand it. You have, say, is gamma minus z. Okay, things are clear now. Please remember that gamma is a variable of integration. And now, this is then Cauchy's integral formula, normal formula. And then suppose what we are going to do, we are going to now do some tricky thing with this. A simple, of course, simple thing, but that will use the knowledge that I have already furnished to you about geometric series. That is, let me recast this 1 by gamma minus z. I will write it as 1 by gamma minus a, and then 1 divided by 1 minus, I will show you that this will be equal z minus a divided by gamma minus a. Now, first of all, let me show that this one is the same thing. But why I am doing this, you will see why I am doing this just in a couple of minutes. But first, let me show you that this is the same. I will take this gamma minus a in the denominator and multiply that by 1 minus z minus a divided by gamma minus a. That if I do that, I have gamma minus a gamma minus a into 1, that is gamma minus a into minus gamma minus a into gamma minus a, that will cancel, and you will have z minus a, that is gamma minus a minus z plus a, and minus z plus a. Okay, nothing actually. Yes, a and a will go. You will have gamma minus z. Gamma minus z is this. You see it. So this is exactly equal to gamma minus z. No problem in that. Now you will ask, sir, why did you do this? Yes, I will tell you why I did this thing. See, look at z minus a. Z a is here. Z is any point in this disk. Now I have shown this z here, for example. This is the z. Z minus a. Divide z minus a and compare this z minus a with gamma minus a. Which of the two size, whose size, modulus will be more? Definitely gamma minus a, because that is on the boundary, z is inside the boundary. So this will definitely be a great, this z minus a is smaller, gamma minus a is larger, because gamma is larger. So it means that this number z minus a divided by gamma minus a has a size that is less than 1. This is less than 1. Okay. Clear? Once more, gamma on this, z here, and then you know everything else follows. Now you have that's okay now. Now this means that this is something like what we already have. 1 minus 1 divided by 1 minus 1 minus, this was our x. 1 divided by 1 minus x. And if you go back and see, remember 1 divided by 1 minus x was c. 1 divided by 1 minus x was sum of infinite these terms. That means I can write if these are infinite terms, I will write them. This is 1 by 1 minus x. These infinite terms sum up to 1 by 1, but with condition. What is that condition? Condition that this x, modulus of x, should be less than 1. If you fulfill this condition, then only this is correct. Otherwise, you will have to write, instead of this, you will have you cannot write anything, because if that condition is not fulfilled, this infinite series will not yield a finite sum. Okay, now with these things, let me then write in. I have there on that page where I'm going, I have there 1 by 1 minus x. I will convert that back into this 1 plus x. Just remember this x, and remember it should be in the formula. You have 1 minus, so x square, x cube, first term is 1, so I will write it here. For ready reference, I will keep it here. 1 by 1 minus x is equal to 1 plus x square plus dash dash dash, provided of course mod x is less than 1. Since you have proved that this is less than 1, hence you can expand now this in as a geometric series. Now, having said that, let's then do that. But since there is there is space, we can do it here. So let us do it. We have 1 by gamma minus z is equal to, you have to keep this thing as it is, gamma minus a. Then this is 1 divided by 1 minus x. X is this, so its value is equal to, you can see yourself what its value is. 1 plus first 1, then x. 1 plus x. X is z minus a divided by gamma minus a. Then x square, z minus a divided by gamma minus a square plus dot so on. And say, suppose, for example, yes, we need to write some more terms. That is, for example, let me write n minus 1th term. You see, if you have first term, the power of this z minus a is 0 there. That is what the z minus a is not there. The power of z minus a here is 1. Here is 2. In which term it has power 2? Third term. 1, 2, 3. Term third, power 2. That means power is 1 less than the number of term. If I write now n minus one term, n minus one term, if I write it, then what will I get? I will get it like this. I will get z minus a divided by gamma minus a divided by gamma minus a raised to I will have raised to n minus 1. N minus 1 for the nth term. This is for nth term. And for n minus 1th term, it will be n minus 2 plus dot dot dot. And there will be more terms than. Now let us we'll consider those terms after this. Suppose now what I am going to do, I am going to substitute value of this into this. This whole thing has to be substituted here. Now in the process, you will have ab gamma into d gamma always there. That I will keep here. I will write this 1 by gamma minus z in front of this. So I will have this situation. What was it? It was integral ab z. Integral ab z. So we have integral ab z is equal to integral ab z is equal to 1 by 2 pi I 1 by 2 pi I integral line loop integral uh, loop integral c f gamma d gamma. Write it here. Now what we have to write? We have to write this. We have to write value of 1 by gamma by minus z. 1 by gamma minus z. It has first component 1 by gamma minus a. First component is 1 by gamma minus a. Okay, next component is sorry, I have to go back. Then gamma minus a. Then this bracketed this quantity that I will here show with braces, these curved braces. And inside curved braces I have first term as z minus a divided by gamma minus a, then square of that, then cube of that, then so on. And I will have this here. I just forgotten it. Z minus a divided by gamma minus a. Z minus a divided by perhaps the first term is not. First term is 1. First term is 1. Sorry. First term is 1. First term is 1. So I have first term as 1 plus z minus a divided by gamma minus a. This is second term. Okay. Then there is third term z minus a square divided by gamma minus a whole square, both whole square plus z minus a gamma minus a whole cube plus dot 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 plus that term that I wanted to show, that is n. That means this term z minus a by z minus a by gamma minus a raised to n minus 2. Or I can show nth term here, then the rest of the terms will be less than this nth term. I can show it and let it be n. And that means I've changed my this. I will take this as nth term. That means if nth terms, then still I have to write n minus 1 there. I'm sorry. I have to write n minus 1 there, and then I will close this. No, I cannot close this because there are subtle terms after this, and I will write for those terms. Yes, I will first close this. Whatever remains, I will write or n for that, or nz. That means remainder. Just we did it in a Taylor's series for these real numbers. Remainder there. Now, obviously, this remainder will involve z minus a raised to n divided by gamma minus a. But then see, if it involves z minus a raised to n, or z minus a divided by gamma minus a raised to n, and if we let then n tend to infinity, this whole thing will go to 0. Why? Because this term is less than 1. It is less than 1. Z minus a gamma minus a less than 1, and when its power goes to infinity, the term will go to 0. That means in the limit that n tends to infinity, I can drop this remainder. Remainder can be dropped. That's okay. Now just remember it, and when we take this infinity, we will drop it, completely drop it. Then we have fz is equal to fz is equal to 1 by 2 pi I, 2 pi I. Now then we have to keep this there where it is, this f gamma d gamma, then multiply this by this. We have there, inside we have 1 by gamma minus a, plus then this is this into this, plus then z minus a raised to 1 divided by gamma minus a squared. Look at this. Now because of this gamma minus a, power of the denominator is 1 more than the power of the numerator, plus then z minus a squared divided by gamma minus a whole cube, plus dot dot dot, plus similarly this nth term and so on and so on. You can think now yourself what it will be there. Now now again expanding it, we have this going back, I have going forward rather, fz is equal to 1 by 2 pi I. Rest I will have to check, sorry, I will have to check here. Integral f gamma d gamma, integral, but I will not write directly f gamma b gamma, this d gamma. I will multiply this first, this with this. It will be f gamma d gamma divided by gamma minus 1. f gamma d gamma divided by gamma minus 1. Okay, then I will have, rather now I will write this here, and then next I will have this into this, that is f gamma d gamma z minus a raised to 1 divided by gamma minus 1 square. You have f gamma integral f gamma d gamma. I am splitting the integral, gamma minus it is gamma minus a, gamma minus a whole raised to n plus 1 into z minus a, whole raised to 1, 2, and z minus a raised to 1 d gamma. Then similarly, if I carry on with this, you have this, I'm sorry I have not written this. Okay, I have that f gamma divided by gamma minus a whole cube, then there I will have z minus a whole, I have to write this d gamma here, and z minus a square, plus integral c f gamma d gamma gamma minus a whole 4 z minus a whole cube, plus dash dot dot. Now we are now ready to finish it, but we will have to use, see this is, you see this is one singularity here, gamma is equal to a, that is a singularity here. There is a singularity of second order here, third order here, fourth order here. Now whenever we have singularities, if the singularity is simple like this, then we use Cauchy's integral formula. But if the singularity is of higher order, then we use generalized Cauchy's integral formula. You have just to do that, and that will be the end of this. But in the process, you can take this z minus a out of this, because z and a are not variables of integration. Variable of integration is gamma, so you can take them out. You can keep them out if you like, and rest then you will apply these Cauchy's integral formulas. Going to new page, I will write fz is equal to 1 by 2 pi I, then repeat these integrals. fz is equal to 1 by 2 pi I, then integral, you have posted this then integral C, integral C, what is it there? Inside in f gamma d gamma divided by gamma minus 1, then this, and one more thing, that is z minus a. F gamma d gamma, gamma minus a, then we have z minus a, z minus a, and then rest f gamma d gamma divided by gamma minus a square. Then we have integral f z minus a whole square, then f gamma d, this gamma minus a whole cube plus d gamma, and similarly for other terms. Now apply now Cauchy's integral formula here. I will keep them these two formulas written here so that it will be easier for you to apply them. One is f gamma d gamma gamma minus a integral c is equal to 2 pi I f a. This is one. 2 pi I f a. Then another is that is this integral, this generalized Cauchy integral formula, that is integral c f gamma divided by gamma minus a raised to n plus 1, because if you have n plus 1 here, then you will get fn here. It is equal to 2 pi I by n factorial fn a. Now use this for this and use this for these rest of them. So we will have fz is equal to 1 by 2 pi I. Then inside we have apply this now. Apply this. This gives us 2 pi I f a 2 pi I f a plus then this. Going to this. Just a minute. Now I have to now use this to by this Cauchy's generalized integral formula. That is, according that, keep this z minus a here. It will, you have to do nothing to it. You have to keep it, retain it as it is. Then use this. So we have the value of this will be 2 pi I. Okay, divided by n factorial. N is n. See, what is n? N is 1 less than the power of gamma minus a. Gamma minus a has power n plus 1. 1 less than that is n. So what is power of this? That is 2. 1 less than that is 1. So it is 1 factorial. 1 factorial. And then fn, that means this first order derivative, because n is less than this. So first order derivative f dash a. Okay, you might have started to have a vision of this Taylor's theorem. This 2 pi I will cancel with this, 2 pi I will cancel with this, and rest. It is becoming clear now. Plus z minus a squared into this generalized this formula, that gives us 2 pi I by n factorial, 2 factorial now. And then second order derivative f2 a, f2a, f1a, f2a plus dot, and you can now understand yourself what it should be. But before writing that, just do one thing. Take this 2 pi I common from all of these, and then we will be left with something very clean. Fz is equal to, we have got it. Fz is equal to this there. 2 pi I and 2 pi I will cancel. fa, then plus fa plus z minus a into this 2 pi I will cancel. Z minus a into f dash a, z minus a into f dash a plus then back again. You have then 2 pi I and 2 pi I will cancel. You have z minus a square double dash a z minus a square f double dash a, that means second order derivative, double dash a plus dash 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 dash. I think you can yourself see now what will be the nth. This was 2 here. Yeah, it is 2. Now nth will be z minus a, then we will have this n here, n, then this of course will be n. And one thing that I forgot, that is you have here integral, see, sorry, this 1 factorial, 2 factorial, then there will be n factorial, n factorial here, sorry, n factorial here is not that. Oh god. Then this here is n factorial. It is here you have, oh, this is our loss. No, this is our loss. Yes, you have here 2 factorial. Here you have 1 factorial, 2 factorial. Here it will be n factorial. So this is the this what I say, this Taylor's series expansion of a complex function. We will return with Lorentz expansion of a complex function, see the difference between the two expansions, and then do some these problems based on these before rushing over to residue theorem. That's all for this lecture. Thank you so much for being with me and hearing me rather patiently. So thank you.